It is January 4th, and this is the libhal biweekly meeting. We actually skipped last week because I wasn't able to make it. All right, so this week we only got 2 items. It may seem kind of like it's going to be a short time, but it actually is going to be quite long. We're going to be going through all the documentation, but there's a couple of major libhal interface changes that I want to discuss. So I had a conversation with Klaus Eagleberger on just the system design of libhal, and during that talk, we had a couple things that we decided that he brought up that he believed were good things to fix and change in the code base when it comes to how we're doing our APIs. It came down to these two things. One is removal of no-except and replacing std function with function ref. It doesn't have to be exactly TL function ref, but I'll go into those details in a sec. So number one, one thing that no-except does, it causes any API to call std terminate, which basically just stops your program, terminates your program, exits your program, if an exception is thrown within them. So if you had some function that was supposed to take a vector and push a whole bunch of elements into it, and a bad alloc was thrown, this would cause that particular exception or that particular function to call terminate at that point. This is in contrary where, like, if no except was not there, that exception would have bubbled its way up to the first catch statement it found. So no except is a bit of a heavy hammer, and it's pretty locked down. Now, if you put no except into something, it allows the compiler to do some particular optimizations here and there. They don't always happen, but they can happen, just giving the compiler the best chance possible. So we did that for all of our APIs, not because we wanted that optimization, that we did not expect or expected no one to actually use exceptions for that part of the code base. But a couple things here. One is that this breaks a rule that the driver does not have the permission to abort a program. That particular responsibility, that permission, is held within the library and driver and application developer. Libraries and drivers cannot abort the system or exit the system at any point in time. And this API, although it doesn't directly do so, it does open up the floodgates for that happening. And that would break one of our guarantees. Another one is this could happen if the driver uses the STL in a way that results in an exception thrown. So even in cases where you don't expect to use any exceptions at all and you have exceptions disabled, if you're in a scenario where you're using, let's say, a vector or a polymorphic vector or something along those lines, and you have an API that throws an exception, this is where a little harder to find. So having no except there is kind of a big thing. And once you go no except, you're kind of stuck with it. Changing out of no except causes a lot of issues throughout down the line. People expect something to stay no except, or they expect it to stay non no except. So that's kind of a thing. You can always add no except later on if you find that it's really necessary, but removing it is a pain. Not code-wise, it's actually really easy to remove it through the code base. It's more that it has effects on people's code. But one of the benefits of doing this is not just the fact that it goes against one of our rules. The other part here is that it allows a broader set of developers to use libhal. Specifically, we had a bit of a rule that we should only use boost leaf and boost leaf result. But the thing is, boost leaf result and boost leaf still work both with exceptions and non-exceptions. So because our code base can work with both, and we'll probably be generating a lot of our libraries that do not use exceptions, but for those who want to use exceptions for their own purposes, this allows them to be able to do that. Let's say they're implementing their own APIs, their own interfaces. They can throw exceptions if they want to, if that's how they want to propagate their errors. The other libraries may not do so, but at least this one could. So in order to make this broader for a certain set of developers, specifically those who aren't working on microcontrollers, but on gigantic embedded machines with lots of resources, where resources are not a problem, they can use that. So that is the removal of no except. On the other side, we have replace std function with TL function ref. So std function is a owning callable object, or it's an owning callable object. In order for it to own the callable, it has to allocate space for it. So usually a lot of function implementations can hold at least 2 pointers. So maybe a pointer to an object and a pointer to like something else, or a parameter, an integer, a register, that kind of thing. So std function can, if it has enough space to hold your callable, such as a lambda or just a function, then it doesn't allocate. But there's nothing in the standard that specifies how much space std function actually has to allocate for itself. Actually, there's actually no specification that it should allocate that it should or should not allocate. It's actually specified that it should allocate the space for your callable object. So you can't depend on compilers just always keeping that number the same and not getting rid of it. And there's no check for that. So using std function means that we will have to, for every API that uses std function, we would have to accept that we allocate. And that is kind of unacceptable. We want to make sure that none of our libraries actually allocate. Yeah. So TL function ref is a non-owning function callable and will never allocate memory. We will rename this to HAL function ref, just so that in the future, if we need to, we can rename that to standard function ref. So we can use the standard version versus using a third-party version. The TL function ref is actually made by a developer named Saya Brand, and they do a lot of implementations of things that libraries they want to add to the C++ library. So it's usually a mock implementation of that. This doesn't change any of the current code, as all users of std function will never were never to own their own callable, just execute it. I wrote this down last time, and actually I've been thinking about this for a while now. That's actually incorrect. We have 3 different drivers that need to own their callable, and that is can, interrupt pin, and timer. All of them you can attach an interrupt to. So having a copy of that thing is critical. Or if you don't have a copy of it, you need to ensure you have 2 options. Either A, own a copy of that particular object, or B, you ensure that the lifetime of that object is equal to or greater than the object of the driver itself. So to give this some perspective, let's say you have an interrupt pin, and you attach interrupt and some lambda. If you're in a function and all you're trying to do is just return that interrupt pin up, so you create a lambda, you have your interrupt pin, you pass the lambda into the interrupt pin, and then you return the interrupt pin. Well, that lambda is now a dangling reference. The lambda is pretty much destroyed. So the pointer that you have for that function ref is pointing to that lambda that doesn't exist anymore. Because of that, when you try to call it, you will get errors, you'll get problems, because it's actually still in that lower stack. That's problematic. So if you're going to do this, you need to package them together somehow, or extend lifetime, or make it static, or make it global in some way, shape, or form. So there are actually some issues here. And I've actually been talking with Klaus, just kind of emailing back and forth on this whole thing. I know the next step is documentation, but I do want to kind of talk about some ideas that I have on this. The main idea I have currently is keep with function ref. Oh, and I forgot to say one thing about why function ref is better than std function. Std function costs about 32 bytes in general. That's its size. It has about 32, a little bit less than 32 bytes in terms of how much it can save in terms of your objects. How a function ref only takes 2 pointers, so it's about 8 bytes. It's dramatically smaller in terms of its footprint when it comes to how big of a parameter it is, as well as how big of an object it is when you try to store it, if you're trying to keep a reference to it. That's one of the benefits. Now, interrupt pin, the thing I want to explain here is, for interrupt pin, one of the things that we could do is function ref still works as it does. It's just a reference to a particular function object. And what you do is you have a factory function, a templated one, that statically allocates each instance of each temporary object or lambda you're trying to create. That would basically extend the lifetime of that object. And then you can pass that into your attach interrupt. That way you can create it locally, but actually store it globally. Global stuff like this isn't usually the best, but because it can be, how should I put this? It can be unique each time. They'll never conflict with each other. There's ways to make that happen. All I'm trying to say is that function ref is going to be the way that we stick with, and the way that you use it with interrupt pin and interrupt pin as well as also timer and can, or anything else that takes an interrupt, would be to use this, what we're kind of thinking of calling extend lifetime. So we're moving over to function ref. There are some new rules on how to use it compared to SID function. SID function, you could do whatever you want with it. It just could allocate, which could cause other issues. TL ref, function ref, has some particular things you have to be careful about. Yeah, I'll probably go more into the solution for a function ref in the next meeting, because that's when I'll probably have an implementation of this. All right, so with that out of the way, we now have documentation. I'm just gonna get right into it. I'm really excited to show you guys what we have right now. I went back to MK Docs. Here's what we have for our documentation. It's just the beginning of it. We are, there's still a lot of things to do. Now, here we just talk about the abstract of what we're really trying to do here. I want to make hardware drivers portable, flexible, accessible, and easy to use. The design philosophy of libhal is to be multi-targeted, meaning that it can work on multiple devices, it can run on pretty much anywhere, so long as it supports modern C++. Lightweight, shouldn't be as complex as like STD function is a bit heavyweight. That's not what I mean by lightweight though, or heavyweight. Sometimes there are systems that are so big and encompassing and really take up so many resources in your system and make you have to use them and work everything within them versus the other way around, that it ends up feeling like you're using their framework versus just using a library. General, should work with most things, like GPIO is a GPIO anywhere. Simple. I know there's some things that in here that implementation-wise that are a little complicated, but I'm hoping that the way that people use this is no harder than using any other language or any other library in C++. Safe, should be where we can be safe. I think TL function ref, SID function is safer, but for performance reasons, we are going to go for function ref. But in most cases, we want to make sure and try to ensure that the code we write pushes people towards the right option. Tested and testable, needs to be unit testable, and needs to be tested. Compiled quickly. It should be, libhal to be compiled quickly. It should be easy to use. It shouldn't take up an enormous amount of time to compile something. And OS agnostic, should be able to be used and also used on be compilable on any system, as long as it supports C++. Used on any system, because we should make sure we can work on any target. So that's pretty much libhal and abstract. We talked about this before, but I don't think I've ever talked about the design philosophies before. So now you guys have that there. Here I have a little section that talks about the basics, what a blinker program would look like just the application itself, the hardware map, the main CPP, the LPC implementation, and also the STM implementation. So now you can see how these different files would all kind of work with each other. I'm going to go into this a little bit, just saying that main is really simple. You run this initialize target function, you get a result back. If the result is not good, then you halt, which means just spin there forever. You can plug in a debugger and check to see where you're at, and you can probably see what had gone wrong, or at least that you got here. Hardware map, you're just pulling out the actual value inside of it. Then you pass this into your application. The application works with the hardware map, and if it ever finishes or exits, that's usually an indication of an error, but we have some things here. So if it's not finished, meaning that there was an error that occurred, and this thing doesn't actually check any errors, you can check them yourself if you like. But if it was not finished or did not hit some type of terminal state, then the system should reset. Otherwise, you can just halt there. You can do whatever you want here. You can choose how you want to do anything at this point. So this is not, this is an example. Here you have an application. You define your application here, returns a status, takes your hardware map, and here we're just blinking. So in the map, we have an LED. I can show you the map here. It's got an LED, a pointer to an LED, and a pointer to a clock, and also a function for resetting. We set the level of the pin to be true, so set the LED state true, delay for 500 milliseconds, and then false, and so on and so forth. And this over and over again. And this should never be reachable for the most part. And then here, you can see where we initialize the target. Now, if you look at the hardware map here, we have these two headers, application and initialize map. Just a function that should return back some map of interfaces. So here we do all initialization steps that we need for our particular system. We grab all the peripherals that we need and we put them into the hardware map. Same thing that happens here, except in this case, the only real difference between these two, besides the actual indexes here and the drivers, would be that, this one initializes that section, this one only does this, and also initializes the floating point unit. That's all you really need in order to get started with libhal. It does seem like quite a few files. You don't need as many if you already have your own project you're integrating into, but if you're starting from scratch and just building a libhal project on its own, this is what you would need. Your main, hardware map, your blinker, and your initialized target classes. You can mix these all into the same place, but depends on how you want to isolate all the different includes. So yeah, that's that. I also have a link to our support. So that's the Discord server, the one that you guys are currently watching this on, for the audience who's currently watching in Discord. GitHub issues, as well as CPP Lang Slack, the embedded channel. And we're also working on adding in dedicated support contracts sometime in the future. And yeah, we distribute through Conan. You can also download directly from our GitHub, but I don't recommend it. And VS Code coming soon. That's pretty much how this whole thing pretty much goes. So I'm just going to kind of look over a couple things. We have setup. So this is like all the setup you need in order to get started for Ubuntu, Mac OS X, and Windows. We have a glossary, so you can see all the different terms here. It's a lot smaller than it used to be just because I kind of compacted things in. Getting started guide is still working on this, so apologies for those who might have been hoping that the documentation gives you everything you need to start working with libhal today. It kind of says that, to start a project, you can go to libhal start, and you have your starter files here. This will actually work if you use it, but I still want to explain all the different parts, how everything works here, so that a user could just read the starter and get an idea about how every part and piece of every single file here works and why it's there. Whoops daisy. So still working on that. And I'm also considering adding in how-tos for how to make a utility library, how to make a device library, and how to make a target library. We do have a libhal library that is the basis library for all these other ones. And we'll also have steps on what you need to do for a utility library, device, and target. Because the work is usually easiest is utility, second easiest is device, and then hardest is target. Now, we have configuration. So this explains how you can configure libhal, such as setting the platform, enabling error callbacks when an error occurs, and stuff like that. Yeah, it explains everything here. We also have finding drivers. This is incomplete. We are actually still trying to come up with a good way of doing this. I have a little explanation on how you should search for drivers. You can also just look at the libhal organization to see what drivers exist there, although even that wouldn't be helpful because a lot of them are made and empty. So you might see libMPU, but MPU is empty. It's just available so that when we start writing code for it, we can just tell people, hey, go to this repo and start adding code there. Conan Center would be a good place to kind of describe how you go about finding it. Just lib and then the name of the driver you're trying to look for, or the device you're trying to look for, but the generic name. And then what I want to work on soon is libhal driver index. I want to create a website that's kind of alongside the documentation that you can go to and search for the drivers that you're interested in. I may make that a part of this documentation here. I may make it its own thing that semi-gets automated out. Like, for example, it takes all the information from those who are using our libhal, what's the word I'm looking for, workflows, our GitHub workflows, and is able to, come up with information about that particular system. For example, let's go to this one here. You can see, where is it? Where's the thing? That's curious. I could have sworn there was a item here that told you who's using you. I could have sworn that was a thing. Maybe if I go here. No. Oh, there it is. Used by. I don't know why it took so long to load up. But yeah, there's a used by area. And it's really cool because you can see all the people that are using our workflows. And I'm like, oh, this is a nice little graph. This kind of tells us, who's losing us. And this doesn't really go deeper, which would be nice if it did. But at least we could know what the libhal libraries are in one way. But yeah. I want to have an index that's searchable. I want to have an index that's organized by category. I want to have an index that is hopefully automated so that your driver just has to make a change on its own repo and it automatically updates. It gets fetched from all the repos get fetched individually and all their data is grabbed that way. Although maybe caching it would be better. Still thinking about how we're going to do this. So yeah, that is the idea of finding drivers. I hope to have this more filled out later. And if anyone else is interested in trying to collaborate and coming up with an idea about this, I would be very happy because I feel like there is a lot of good ways to do this that could really make the entire ecosystem look so much better. Actually, I'm going to talk a little bit on that, how much time I got. Yeah, quite a bit. There's having good libraries. There's having a good software practice. There's having unit tested stuff. There's having stuff even that's fuzzed. You do all the right things. And even if your code's actually relatively easy to use, if people have a hard time navigating it or just finding the things that they need to get going, and that becomes a bother, that becomes a burden for them, they may consider the next best option that does have this stuff set up for them appropriately. Here's one good example, Arduino. Arduino has a really easy to find index of all of their packages. You want to program for the ESP32, you just type in ESP32 and boom, you're ready to go. You have a particular device that you're looking for, you just click inside their package manager, their own package manager, and you'll find it. If you don't, then you're struck out of luck. You may have to do things manually and actually download it from GitHub. A lot of times, the ecosystem they have is pretty well put together. We need to have that same amount of ease, that same speed when it comes to looking up the index, that same feeling of all I need to do is just know the parts that I'm looking for, and they should just pop up. Ooh, one other thing I wanted to add is tags. It'd be great to have tags in there, such as, I think the only really good example we have of tags would be, let's see, repositories. I think it's libarm Cortex. Beautiful, yes. We have microcontroller, embedded, Cortex-M, embedded system, Cortex-ARM. Having all these tags here will be monumentally important and useful to making sure that users can find the parts they're looking for, even if they're putting in names that may not be exactly what the library's name is. So that's that part. I'm also going to go through design documents. I might change the name from design documents to, I'm not sure what to really call it, but I find that design document sounds like, oh, for people who are maybe wanting to get into the weeds, even contributors don't even look at it. Like, only people who look at it are the people who need to understand how to fix it or change it. I want this part to be made more important. And maybe that's just me putting in design, like moving all of this stuff out of design documents and putting it in its own level. Yeah, let's get into it. So this really just explains what design docs are. Design philosophy. I already kind of went over all these parts here, but you can go in here and read them to know what we design around. And if you see violations of these things, bring it up, make an issue, or bring it up on the Discord. It'd be great to see if there's any parts here that don't fit, because either A, or either number one, that simply means that we need to go and fix that code, or B, or number two, we need to possibly reconsider some of our design philosophy. Yeah. Architectural design choices is also another area here, which is going to be really helpful for you to understand why certain things are the way that they are. There might be some weirdness in libhal that you see, such as soon enough we're going to be using just structures for return types. Like every single return type for a libhal API will be a structure, and that is to allow you to expand it in the future. It would be an ABI break, but we don't care about ABI. We always rebuild the world. So we should be able to do this and not break people's APIs. And you can see a whole bunch of other things here, like why we use tweak files, why we're header only, encapsulated memory mapped classes and why that's important, function ref over function. And also this idea came from Klaus. He actually helped guide me on how I should go about designing this out, and also putting in these letters and numbers to kind of make it more official. So I can say, oh yeah, if you're looking for this information, it's in A6. Look in architecture design A6. These are permanent links too, so you can link them to people. Strongly leverage package managers, foundation, yada, yada, yada. Boost leaf for error handling, that's a big one. Using statement expressions, which are not portable. Why we do not use fixed point. I think if anyone's been here for that talk, that was a big, long journey, and so on and so forth. Yeah, so that's the architectural designs. Go down to style. You probably already see, if you've seen libhal, you know the style, but I kind of define it out more here. Get some examples here as well. And yeah, so that's defined here. Interface building blocks talks about like result, status, units, timeout, and soon enough will be HAL function ref, because I think we're going to build our own implementation because we want it to be as close as what standard function ref is going to be like, but also potentially adding some other features in that we think are necessary. Last but not least, or second to last but not least, We have interfaces. We have ADC interface. We have DAC. And these pretty much just describe these particular interfaces and why they're designed the way that they were. So in this case, we have SPI, and we're kind of describing. And to note, the way I'm going to do these interface designs, they're going to be kind of, I don't know the right way to put it, but let's say negative. And by that, I mean, they aren't going to be explaining why we chose certain design, why the API is what it is. We're going to explain why it's missing certain features. And if people want to know why the other interface is what it is, sure, we can do that. Just, it's kind of obvious. That's how SPI works. You have to transmit some buffer, you have to receive some buffer. I may describe why we did that in particular, but it's more of a defense. Each one of these interfaces is more of a defense of certain aspects of the interfaces. For example, 8-bit frames. Why do we choose 8-bit frames? There could be 4, 5, 6, 8, 7, 9, 10, 11, 12, up to 16-bit frames for SPI. Why do we choose 8-bit frames? Well, because almost everyone uses 8-bit frames. And trying to support a multi-sized frame interface is going to be useful for only a very, very small set of people, small set of developers. So we don't include it. If we find that there is demand for it, we will make another interface specifically for what I call it variable frame SPI, just for that specific purpose. So you pay for the cost of all the shenanigans you have to do to make that work. And hopefully, most cases, you'll never actually even need it, and we'll never actually have to implement that particular thing, but we will implement it if it's necessary. I2C. Not really much happening here for the most part. So yeah, you can see a couple of things here. Some of them might have some content in them, but aren't actually done yet. So if they're crossed out, that means they're not really ready. If they're checked off, you can read them. And then last, we have the About Us page. So that's the documentation. Oh, I'm so sorry. I haven't shown you guys the more newer stuff. This is from the website, but I'm still working on some other additional things like the organization of libhal, so that's a little easier for you to read. And I'm actually going to show you this now. I should have pushed this up more recently, but I still need to add more items to this. So here we have the architecture, the layout for target libraries. I may shorten this down just a little bit, just so that it's easier to fit on one page. But the main thing is that you have libhal. You have this category of processors or processor libraries, and you have libhal Linux. I'm not calling it liblinux because I think that that's a really bad name to put out there. That's going to confuse so many people. So libhal Linux, librisc5 MCU, and then libarm Cortex. And you can see that this is adopted by is depended by on, I don't know how to pronounce that, but basically, liblpc40xx depends on libarm Cortex, libstm, same thing, so on and so forth. And that pretty much be the order here. Then you look at the device libraries, which are different category libraries. These only just take in libhal. That's it. They only depend on libhal. Libhal soft, MPU, ASP, DRV. They really shouldn't need anything more than that. There are other types of libraries that we are going to consider. One of them is going to be processor libraries, which I'm considering as well. Basically, or process libraries or application libraries. I'm still trying to figure out the right name. I realized that you could make an application. So rather than just making a library, you can make an application that's also portable. There's no reason why you couldn't just define your own hardware map and say, I need these things. Like, for example, we were thinking about the idea of a game called Pong, or I'm sorry, not a game called Pong, but making our own Pong. And what do you really need? Well, here's a little typical application. You need an LED matrix, because why not? Let's use the LED matrix for this game. We're using STM32F103, so we need to use this library. And then we want to use a Wii remote, 2 Wii remotes to make this thing work. And all these are dependent on, Apple depends on. And this may be like the relevant Conan file. So that's how everything kind of changed together. But then I thought to myself, well, couldn't you say that all I really need is something that implements this controller interface? Maybe I define it. Maybe my Pong game defines that one. It needs these buttons, and you can implement those buttons however you like. I just need to be able to check it and update and refresh every so often. Lib matrix. What do I really need a matrix? What is a matrix more than just being a simple, really big LED display? So I just need a display. And that's pretty much it. If you give me a controller and display, I can play you Pong, right? So I realized that you could pretty much make a Pong application On its own, that like does not require any particular drivers. You just have to give it the bare OS or the bare hardware interfaces, and as long as you gave it the right things, those things work, then you're fine to go. So all that needs to happen is someone needs to take that particular library, download it, call its only function, which is Pong, and run it. If you think, okay, well, why would we do it as a separate library? The benefit of that is that that means you could run it as a processor inside of a thread. So you could literally put it on its own thread, let it do its own thing. It's all encapsulated, so you don't have to worry about any sort of mutexes or other issues like that popping up. You don't have to worry about, any sort of collisions unless the two processes use the same thing, in which case there's ways to get around that, but I'm not going to get into that detail. But for now, you have these different processes that you can run in your own separate threads. So you could have 3 Pong games working if you wanted to. You could also have, Pong working as well as something else. I'm not sure what the other thing would be, but you have a whole variety of things running at once. And I think that's really neat. And if we get coroutines working really well, we might be able to do that without needing an OS in the background either. So that I think is about it when it comes to the documentation. And another little cool thing is that you can also see the number of stars we have, the number of forks we have, and our current released version appear as well. I plan to also version out the documentation so that each time we upgrade the version, if people need to, every time the documentation updates, you can go back to older versions of the documentation. So I'm hoping to work on that. I don't know if that's going to be out anytime soon, but maybe later on when we have extra time, we will work on that. All right, I think that's pretty much it.